All right, hello. My name is Jonathan Goklowski. I am doing part of the presentation on chapter 14.3, and that is the conversion of our integrals into polar coordinates. Now, we've been looking at problems that look pretty much something like this. I'm going to draw a quick problem. So we'll be given a couple of different equations. Say you're given y equals negative 2x plus 5, x equals 1, x equals 3, and let's go ahead and just graph this out really quick. And what we're going to be doing is we're going to be finding the area of this bounded region right here, also y equals 0. So that way we go ahead and do that. So in this bounded region right here, we're going to be finding the area, and we've been doing it in chapter 14.3 with double integrals, right? So standard of our integrals, at least how I'm going to do it. Of course, much of this is going to be just how I go about problem solving. So far, it's worked for me. But we're going to go ahead and start by drawing out our standard format and then taking a look and setting our bounds, which is really what problems like this are going to be set up for. You're going to be looking at it, draw your procedure is going to be draw your graph from the equations you're given and find your bounds and evaluate the integral. Now, for this one, it's fairly straightforward. We're just going to be taking a look at our bounds. We're going to look for dy dx first. So this one's going to be, we're probably going to expect an equation to be one of these bounds, and then the outer bound is going to be probably just going to be constants. So looking at it in terms of y, we're going from y equals 0 up to y equals negative 2x plus 5. So we're going to go ahead and put that for our y bounds. And then for our x bounds, we're going from 1 to 3. Super easy evaluation. We would, of course, just evaluate it at y. I'm going to save the time and not draw that out because that's not what this section's about. You can evaluate that very easily, and we would have no problem. Now, that is because this is a very, very simple integration. Of course, if there are plenty of other harder integrations that we could do, but we're going to look at other problems that might give us trouble, and especially for 14.3, things that look a little bit more like this. Now, let's say that I'm looking at this shape right here. And this is going to be set by the equations x squared plus y squared is equal to, say, 9, right? And x squared plus y squared is equal to 1, okay? Which means that we've got two circles here, and then we're also going to say x is equal to 0 and y is equal to 0, which puts us just in the first quadrant here. Now, we can take a look at this, and there's just this drawing right here, just this region right here. If we do it in the same way that we've already done this integral over here, it's going to give us a little bit of a trouble because what we're looking at here, so this is going to be 1 and 3, of course, and same over here. The issue is, of course, that we get to this, we got to split it here, and maybe that's not so bad because we're just looking at this. But what if we start looking at problems that get a little bit more messy? Maybe something that doesn't have nice smooth curves. And we're already splitting it 2 here, which is more work than I'd like to do on a problem like this, especially once we learn how to do polar coordinates. We're looking at something that is bounded by a region by a line like that and one right here, and then it's got a waviness right here and a wavy right there. We're looking at Lord knows how many different splits for this one just to get it to be kind of a reasonable evaluation. I don't want to do that many regions. That's a horrible mess. So that is where the next version of our kind of solving these problems comes in, and that's what 14.3 is all about. Because looking at problems like this very simply looks like a section of a circle, a quarter of a circle. And if we look at it that way and we change our coordinates to be, rather than just being in the cardinal x, y, and z when we get into the third dimension, rather than looking x, y, and z, we look at it in terms of radius and theta. So it makes it much easier that way. So let's go ahead and first I want to just kind of take a quick look at the calculus, the calculus behind these kinds of problems. Now, when I do the math, much of this goes right over my head in terms of the very specific equations. So I like to think of it in more of just kind of practical, straightforward terms. So when we're looking at, go ahead and draw a simple recreation of that first integral, right? We're looking at, when we learn the fundamental theorem of calculus, you're looking at things that, you're drawing your Riemann sums of your rectangles like this. And when we get into double integrals, we're going to be essentially drawing a bunch of little squares in this area, correct? So we're going to go ahead and just kind of draw that out really quick, really rough sketch of what that's going to look like. And the idea is that each one of these is going to be a part of, we're going to use these as sort of a Riemann sum to find the area of this space. And the smaller these rectangles get, the better it's going to fit, and the more accurate are, as the infinity of as the size of these squares approaches 0, taking limits. Really, most of that is just stuff that we've gone over in pre-calc. So that makes this evaluate out to be essentially the area bounded within the regions. Now, when we try and it fits really nicely in this area, there's barely any extra space, and things work out nicely when it's a nice, fairly straightforward shape. But when you get into these rounded shapes that you get with circles, things start to get weird when you try to put squares in them. I just, plain and simple, think that squares don't fit in circles. Squares can fit in other squares and rectangles and other kinds of shapes like that. But when you get into circles, it's easier to look at it in terms of arc segments. So instead of drawing us all these ridiculous, squares and hoping that most of them fit, and trying to fit them all in, of course, I'm drawing that very ineptly. But if we look at it more in terms of small sections of the circle, in terms of polar sections. So say that we've got this little section right here of a circle. I'm drawing a very rough sketch, of course. A very rough section of the circle, and we cut it, rather than rectangles, we cut it into, because as you can see up here in these are in terms of, the vertical lines of this graph is in terms of, y, and then the horizontal in terms of x. And if we look at it, because that works in the system where x and y are very clear calculated equations, but when we look at the arc lengths and things like this, or areas in circular radial shapes, it's much easier to think of it in terms of radius and theta, of course, so angles and things. So if we split it, this is, all of these come out to, different radiuses. This comes out to, radius A, B, C, whatever. These are all little different delta radiuses, right? Each line I've drawn here is a smaller radius. And the distance, and then if I come in and I draw the other lines, making it, sections of the polar coordinates, these here are our thetas. They're going to be different angles. I know it's a very rough sketch, but simply put, when we want to look at shapes that are better evaluated, or especially when they're expressed in terms of radius, or in terms of, especially when you work with cosine and sine, it's a lot easier to work with them in polar coordinates. So what we're going to do is we're going to take this same equation, this first very simple one right here, and we're going to convert it into our polar coordinates. So we're going to go ahead, let's just start down here and draw that again, make it nice and easy. I'll skip drawing the equations and just draw the simple graph, and then we'll look at it in terms of polar coordinates. So if we're looking at it, this is, as always, we're going to be looking for the bounds, right? So we'll start with our bounds. I'm going to be going from, instead of from up here, we were looking from x and y, where x was, I probably should have written it like this earlier, but x is from 1 to 3, and y was from 0 to negative 2x plus 5, right? Now, if we're looking at it in terms of radians and theta, right? So if we're looking at it like this, let's go ahead and do theta, because this is pretty obvious to me, at least. I of course, in math, you always have to be careful when you call something obvious. But this is, of course, 0 or 2 pi. But we're going to go with 0 because we're only going to be looking in the first quadrant. Doesn't matter if it goes all the way around. And then up here is, of course, pi over 2. And so if we're going from there to there, it's just from 0 to pi over 2, which is nice and straightforward. And then right here, we've got the radius, which is going to be going from, as I listed earlier, from 1 to 3, which means that our points of integration, our bounds are very, very straightforward. That's awesome. So we're going to write it just like this, 1 to 3, and from 0 to pi over 2. Or, oops, sorry, I got that backwards. From radius is 1 to 3, and from 0 to pi over 2. Because when we write our bounds, when we're evaluating this, it is from dr d theta. Okay, so evaluating this is really great because it's just a straightforward problem. We're just looking at this this equation. I'm sure everyone, if we have a standard understanding of the integrals up to this point, this equation won't be much harder. Now, if you'll notice, I wrote r here. And whenever we convert, whenever we're going to convert from standard x, y coordinates, x, y, z, we're going to convert to polar, we have to make sure that we add in a r. Now, the reasoning behind that we go over later when we get to Jacobians, but for the most part right now, just simply put it, evaluate your equation convert it in polar, make sure that you put that r, because if you don't, you're going to evaluate it incorrectly. Okay, so with everything that we have there in terms of how to do the converting of a problem, let's look at a really, really simple one and actually try it out, because I'll tell you right now, I can hear the discussion of a math problem all the times that I want to, but it's always going to make more sense when I actually see it done. So let's kind of take a look at that first one that we kind of looked at, and we'll evaluate it. We'll change a couple variables, make it a little bit more tricky, but we'll actually evaluate it and see what it looks like. So like we had shown, let's say that we have two circles as our bounds, as well as, oof, that's a very, very bad circle, as well as a couple of angle bounds. So let's kind of a little section of an arc. So let's say that this is the angle pi over 3, and then the angle pi over 6, okay? So these are our bounds. So theta, so we're going to go ahead and take a look at it. Let's say that this graph right here is x squared plus y squared is equal to 25, right? And this one, x squared plus y squared is equal to 4, okay? So if you, like we had mentioned before, if you try and evaluate this just straight out, trying to solve for x and y and finding your bounds, it's just you're gonna get some square roots in there, and you're gonna be adding in pi, and then you're gonna be evaluating with that. That just, I'm sure you could do it if you really want to take the time, but this, if you put it in terms of polar coordinates, is going to be just far, far easier. So let's go ahead and do that. So we'll look at it. We're going to set up our problem, make sure we put that r in there. This is how I do it, just to make sure that I don't forget it. I make sure that r is in there right away, and I draw out my dr d theta, okay? So what are our bounds on r? Pretty straightforward. We're looking at this equation, right? If we were to convert it, if you were to actually do polar conversions of x equals, you know, r cosine theta, and y equals r sine theta, you plug that in, you know, you've got your r cosine theta squared plus r sine theta squared equals 25. Evaluate that out, you're going to end up with r squared is equal to 25, r is equal to 5, right? And I'll do the same thing for the other equation, r would be equal to 2, okay? So that means that our bound for our radius, at least, is from 2 to 5, right? If you look at it pretty fundamentally, when you start to recognize what circles are, especially in this chapter, you're going to see a lot of this kind of setup, and you know that that's, you know, your radius squared. So we're going to go ahead and we've got that for our radius, and we're going to do our theta now. So theta is very straightforward. It's pretty much just given to us, right? So it's from pi over 6 to pi over 3, okay? And we are going to go ahead and plug those in as our bounds. So we've got from dr d theta, so it's going to be r is from 2 to 5, like we said, and then theta is from pi over 6 to pi over 3, okay? Now, evaluating for that, we've got, I'm kind of a mental math. Let's see if I can actually speak this out. So evaluating, you know, integrating r, it's going to be r squared over 2, simple power rule, evaluated from 2 to 5, right? And we've still got our pi over 6 bound, pi over 3, d theta. So we're looking at 25, oops, not 25, 25 over 2 minus 4 over 2 d theta. You go from pi over 6 to pi over 3, coming out to 21 over 2, right, d theta, and evaluated from pi over 3 to pi over 6. Just evaluates out to 21 because it's just a constant, 21 over 2 theta, evaluated from pi over 3, pi over 6. And I'm sure that everyone can figure out plugging this in and then subtracting. I'm going to go ahead and save time there. If you really want me to, 21 over 2 of pi over 3 minus pi over 6. If you can't figure it out from there, I'm concerned as to what you're doing in multivariate calculus, to be honest. So that's what happens when it's a just nice straightforward circle. Now, like in the section before, we had problems that were, when we were looking at, you know, xy coordinates, we had problems that were vertically simple, right? Where the bounds from left to right were just straight lines, and then the top and bottom were the tricky ones. You know, you've got some stuff going on. Where if you were to try and, let's make this a little bit more of a drastic shape, right? So vertically, it's very simple from, say, A to B. And you've got this super wavy line, right? Which if we try to draw it, you know, horizontally, this would just be all these little sections that are just terrible. But of course, vertically speaking, let's draw the bottom part too. Vertically speaking, it's very straightforward. Just straight lines. Everything's in its own little section with the bottom part being whatever f of x is here, and then the top bound being whatever g of x is. So this is vertically simple, right? And then the same thing for horizontally simple. You've got your lines and you've got your wonky shapes, and it's much easier to do it in terms of horizontal, right? Which is why, here you would do, dy dx, because it's, vertically simple, but here you do dx dy, okay? Because it's horizontally simple. Now, same thing happens with our polar coordinates. We're going to have situations where, say, your equation's going to look something like this, where you've got your nice, straightforward angles drawn out, but your functions are weird and wonky. Now, if we were to evaluate this without converting to polar coordinates, that would be a nightmare. Lord knows how many different sections you would have here, right? But fortunately, this is what we would call theta simple, right? Because your angles right here, say this is like I just said before, pi over 6, pi over 3. You've got a very simple angle, and it's just the radius that's difficult. And in this case, you want to make sure that you integrate properly with respect to that. And here, let me just go ahead and draw this out for the other one as well in case of radius simple, right? So you've got your radiuses that are nice, but it's your thetas that are wonky, right? So when we're looking up here, right, it's the y values that are wonky and the x values that are simple. So you want to put the y values first and then the x values second. And then here you've got the x values that are wonky and the y values that are simple. So if, obviously, so you integrate the one first that has the wonky, variable, the equation that is involved, right? That's really what we're doing when we're doing our double integrals. We want to make sure that the innermost integral has the equations involved so that we're just dealing with constants when we get to the outer one. So if we're looking at these problems out here, right, say that this is given by g of x and this is given by f of x, okay? And we'll do the same thing. I'll just go ahead and save time and write that out over here. So from f of x and g of x, okay? Say that those are what those lines come from. If our theta is simple, right, we want to make sure that we integrate with theta last, which means that we want our radius to be first. So radius is from, f of x to g of x, and then from pi over 6 to pi over 3. Nice and easy. And you, of course, don't forget the r. Make sure you don't do that. Don't forget your r. Evaluate that out, whatever those equations are. It'll come out nice and easy. Well, assuming that your equations aren't too nuts. And same thing over here. But because we have the thetas that's complicated, we want to make sure we can integrate that first because that's what the function's going to be. R dr, and then we're going to evaluate from same thing, f of x, g of x, and from radius, say that this was 1 and that was 3. So from 1 to 3. And from there, it really is just straightforward integration. A lot of this chapter is just going to be making sure that you've got your bounds right, and then just integration. Standard integration rules, know your u sub, integration by parts for the tricky ones, all kinds of different substitutions, trig subs. But for the most part, you want to make sure that it's this part that you set up right. If you set up your bounds properly and you integrate in the proper order, your problems are going to go over much nicer than if we try and do it the way that we have been doing before. So keep an eye out for anything that's going to indicate some kind of something that would look better in polar coordinates. Always keep an eye out for that because it's going to save you a lot of time and a lot of stress if you just convert things like this into polar coordinates. Last notes, just to kind of simplify the most important things to take away from this section. You want to make sure, do not forget R. Do not forget R. You want to make sure I guess I should write that in lowercase. Because when you are converting to polar, you are changing things. Okay, so you need to make sure that you do not forget the R. If you end up doing things that involve, plugging the function and not just finding simple area, if we start involving in density and things like that, or, anything in that nature, you start plugging in functions in this place too, don't forget to distribute the R. And then secondly, make sure you set up your bounds. If you can set up your bounds properly, those two things, those are your fundamentals for this section. If you can get those right, you'll be in a pretty good shape.